Hello everyone. One more example of taking Newton's first law, which are balanced forces and constant velocities, and applying it to specific situations. And this one is a device called a modified Atwood's machine. It's named after a guy named Robert Atwood, Sir Robert Atwood, an Englishman. Um, Basically, it consists of a cart, or in this case, to keep it simple, a box on a table with a string running over a massless, frictionless, perfect pulley down to a hanging mass, right? And when you let them go, they kind of move together, if you can imagine that, okay? This is actually a setup we're going to use at least once, maybe more, in a lab this year. It's kind of a handy thing. A full-on Atwood's machine just has a pulley with the two masses both kind of hanging and vertical, so they go up and down, right? The thing that makes it modified is that this one is on a table. Okay, so that's why it's a modified Atwood's machine. But it's kind of a traditional little physics device that gets used quite often in lab situations. Good example of some of Newton's laws can be seen on here. And yes, this is what we call a massless, frictionless pulley, so that basically we can ignore the effects of the pulley. Okay? As you'll see when we do this in lab, we have some pulleys that are very, very low friction, and they're made from plastic, which means they are very low mass compared to what we're going to put here and here. So we can basically ignore them, right? So it works that way. We can actually create that in lab. All right, so I want to look at kind of what's going on in this situation, and then, of course, use Newton's first law to be able to make some predictions about things. So we're going to start out. There's actually two ways we can approach this modified Atwood's machine, two methods, if you will. And by the way, this one's moving at a constant velocity. You see that? Right? So it's going to move this way at constant velocity till it, hits the pulley, breaks stuff, and makes me angry. But method one is we're going to treat these two objects as if they are separate objects which are tied together by a string. You might say, well, isn't that what we have to do? No, but that's method two. We'll get there. So we're going to treat them as two separate objects. So first off, let's do a little system schema here. To distinguish between the two objects, I'm going to call this one A, this one B, just to give them an extra subscript so I know which is which. So again, the one on the table is A. It's got a mass of 5 kilograms. The one hanging off the side is B. It's got a mass of 2 kilograms. All right? So here's box A. So what interactions does box A have? Well, of course, it interacts with the Earth through the force of gravity. Now notice here, I need to distinguish between the weight of box A and the weight of box B. So I'm going to call this one F of G A. Extra little subscript is important there so we know which is which. Okay? It also interacts with the table, which supports it. That, of course, is a normal force. And since the question asks about what force of friction must exist, well, that means that there's more going on between the box and the table than just support. They also must be rubbing against one another with a force of kinetic friction. Kinetic because the box is going to be moving, sliding, if you will, across the surface. So two interactions there. What else is the box interacting with? Well, the string. And that, of course, would be a force of tension. Anything else interacting with box A? Is box B? No, right? It doesn't touch, push or pull on A, right? It does with the string, and the string pulls on A, but right, that's a level of separation there. So this is it for box A. But now let's throw in box B into our system schema. What does box B interact with? Well, of course, it interacts with the Earth through a force of gravity. Notice the extra subscript. This is the weight of only of box B, right? So box B is interacting with the Earth, and so is box A. So make sure you got your subscripts. Now the table isn't doing anything to B because it's hanging off the side, right? But B is interacting with the string through a force of tension. Now, you may notice here that I did not put force of tension A and force of tension B. Okay, I did that because this is just a single string going over an ideal massless, frictionless pulley. So it can only exert one force. Right? It can't exert one force on one end and one force on the other end. It couldn't move at constant velocity then. Right? Things wouldn't be balanced. So because we're dealing with this situation, an idealized kind of situation with a massless, frictionless pulley and one string. It's not a whole big block and tackle system with a bunch of pulleys that the string is wrapped around, okay? This is the same force of tension here and here, at least size-wise, which is why I don't have to distinguish A or B, okay? So that's it. So we're going to treat them as separate objects. So there's A. Notice A has 1, 2, 3, 4 interactions, and therefore 4 forces. Whereas box B is simpler. It only has 2 interactions, and therefore 2 forces acting upon it. It's a little more complex of a system schema here, as we have 2 objects we got to keep track of. So let's make 2 force diagrams. Here's box A, here's box B. Now, I could put dots, but then it would be hard to tell which one is which, right? So I'm going to, draw a little representation of box A and box B. So A has force of gravity acting down. Notice the extra A. Normal force acting up. How big does that normal force have to be compared to F of GA? Yeah, they have to balance, right? Because this box is not even moving up and down, so it has a constant velocity of 0. There's the force of tension to the right from the string. There's the force of kinetic friction opposing that motion, so acting to the left. How big do those forces have to be? Because it's moving with constant velocity, they have to balance. But are you okay with that one? Now notice, this is, we're trying to find the force of friction here, right? We just found out that it's balanced by the force of tension, but we don't know what the force of tension is. So we can't solve the problem just by looking at box A. However, we've also got box B. It has a force of gravity acting on it. Notice it's smaller. It's roughly 2/5 as big, right? So make sure your arrow is smaller. And that's F of GB. And it has a force of tension from the string, which will, of course, act up. How big does this force of tension have to be compared to F of GB? Well, it's moving at a constant velocity, so they have to be balanced. Now, I do want you to notice here that these have to, in order for the 2 tensions to be the same tension, this force of tension has to be just as big as this force of tension, which means this arrow has to be the same as this arrow, and this arrow has to be the same as that arrow. Right? So if you're really drawing your force diagram well and thinking through what has to be true about it, all 4 of these arrows should be the same length. They should all be roughly 2/5 as big as that one. You're probably already seeing how we can then figure out how big friction is, right, from doing this, but I'm going to write it out here in a moment. Everybody okay with that? As always, drawing out properly labeled force diagrams where you are thinking about how big the forces have to be relative to one another, applying Newton's laws to those situations, is vital for being able to figure out what's really going on in the situation. It's the physics, folks. So, if we start out here with the box A, all right, we write the horizontal equation for the horizontal forces for box A, right? We know these 2 have to be balanced because it's got a constant velocity. But that doesn't get us anywhere, right, because we don't know the force of tension in the string. But we can do that same thing for the vertical forces acting on box B, and those have to be balanced because because it's moving at a constant velocity. And again, since it's a single string on a single massless, frictionless pulley, those forces of tension have to be the same. But remember, we need to be able to calculate the force of gravity acting on B, and we don't know its weight, we know its mass. Right? We know its mass. And therefore, we have to break down F of GB into mg, mass times gravitational field strength. Note here how I put a subscript on the mass. That way we know which mass we're talking about, because in this case they happen to be different. They don't have to be, right? But in this case they are. So we need to make sure that we add the subscript there. So again, this is mass times gravitational field strength. If you want to find out the weight of box B off to the side, feel free. I like to work symbolically. So we plug it in, and that's how we can find the force of kinetic friction. Plug in the numbers. It's 2 kilograms, 2.0 kilograms, right? and 9.8 newtons per kilogram. Notice the kilograms cancel and we're left with newtons. 2 sig figs, 2 sig figs. So 2 sig figs in our answer. It's really 19.6, but 19.6 rounded off to 2 sig figs is 20 with a decimal point, right? So that the 0 counts. Okay? Don't, be careful with the sig figs here. So 2 sig figs, 20 newtons with a decimal point. Notice here, it's kind of interesting, but the mass of the box here doesn't really seem to affect it at all. We could have a 10 kilogram box A, and we would still need the same amount of kinetic friction in order to keep everything moving at constant velocity. Interesting. Okay, so that's one method. Requires us to write 2 equations and kind of solve them together. Here's the second method. A little bit tricky, but it makes the math easier, all right? So if you can get through the conceptual aspect of it, it'll help us do the math. And believe me, when we get into situations where these are moving without a constant velocity, where it's speeding up or slowing down, we'll have fancier words from that later, right? This method, method 2, is way easier with the math, okay? Way, way easier. So I'll try to introduce it to you here. And that is that since these two things move together, because they're tied together with a string, why not treat them as if they're one big thing? As if we have this is our system, right? Is both boxes in the string together. You with me? I mean, we've been doing that all along. Right? If we're dealing with, say, the toy car lab, we didn't worry about the various parts of the toy car lab, right? We just said, of the toy car, we just said, it's all moving together as one big thing. So let's do that here. We'll treat this as one big thing. Now, where does that help us? Well, notice that the forces of tension are now inside our system. And therefore, we can basically ignore them. Right? We can ignore those forces of tension. Not that they're not there, they obviously are, right? But we can ignore them as far as our force analysis goes because they're between the parts of our system. It's like the forces between atoms of this box, right? We don't have to worry about the forces between the individual atoms. Okay? We can just deal with the box as an object. Well, it's the same thing here, right? So since they're internal to the system, we can ignore those interactions and only focus on what we can call the external interactions, the actions that occur outside of our system. And like I said, whether you know it or not, we've been doing that all the time, right? Because we've just said, this is a box, or this is a cart, or this is a water bottle, or whatever it is. We haven't worried about the pieces of it, right? We've just put it into one big thing. That's the tricky part, okay, is the conceptual part of doing that. Now, this is going to require us, so recognize then, if we can ignore the force of tension interactions because they're internal, there are 1, 2, 3, 4 external interactions going on with the system, and therefore 4 forces acting upon the system. Okay? Now, we do have to be a little clever with the force diagram as well. Rather than drawing, say, a single dot for the thing, which we could get confusing, we're going to draw a system force diagram. Okay? Basically, what I'm going to do is I'm going to ignore the pulley. I'm going to pretend like it's not there. I'm going to pull this box up next to A, at least in our heads, in our force diagram, okay, and draw it that way. This is what I mean. I'm going to draw it like this. See what I did there? I took this and slid it up next to here as if it was all one big thing moving together, yeah? The little dotted line is like our green dotted line on our system schema. It's the system boundary. And we don't worry about things that happen inside. So while there is this string here, we're not going to worry about those forces of tension because they're inside of our system. Okay? And I turned this to its side for a reason, and you'll see why in a moment here. So let's start out. We know there's a force of gravity acting on A. That would act down. Right? And notice the extra little subscripts so we know which is which. There's also a force of gravity acting on B. Okay? But here's the tricky part. What direction does it act? Now, in real life, It acts down, of course, right? It would pull down here, which is actually the force that is towing both masses. The concept builder guy calls that the towing force, right? It's the force of gravity here is what's making both of these move, right? Without that force, friction would slow it down to a stop, right? But on our diagram, our force diagram, we've pulled this one up next to it. So do you see what direction it will act? And our diagram, we have to draw it to the right to keep it consistent with this acting like one big object. A little tricky thing. That's why I drew this sideways, right, to make it a little easier for you to see what we were doing, right? We drew this and dragged it up here, okay? There is a normal force acting on box A. Box A is not even moving up and down, right? And therefore has a constant velocity, so those have to balance. Then there's a force of friction acting on box A, which will oppose its motion. Since box A moves to the right, friction will act to the left. And here's the good part. How big does this force of friction need to be? Well, the whole system is moving with constant velocity. Therefore, all of the forces need to balance. And since these are the only two horizontal forces, they have to balance. You okay with that? All right, so we're ignoring these little forces of tension because they're inside of our system. And so this cuts through kind of the using the force of tension as the middleman. And like I said, it's not a big deal in this unit, but when we deal with this same modified Atwood's machine, but it's speeding up or slowing down, and we have fancier words for that we'll use later, right? It's going to make the math tremendously easier. Because now we can just write one equation and say, oh, friction's equal to F of GB. F of GB is the mass of B times the gravitational field strength, 2 times 9.8, 20 newtons with a decimal point to 2 sig figs, and we're done. Right? We don't have to mess with that. This is equal to the force of tension, and the force of tension is equal to that, and therefore they're equal to one another kind of thing. Right? We can just do this straight out. So this is a little trick, if you will, of looking at things as systems, right? Objects that are moving together, so we treat them as if they're moving as one big thing, as opposed to treating them separately and looking at them as two separate objects. So you might be wondering then, why would we ever look at them as two separate objects? Well, we would only look at them as two separate objects in this kind of case, all right, when we can ignore the pulley and everything, if what we wanted to know was the tension, right? Looking at them as one big system ignores the tension, and therefore it's not part of the problem, right? So if I wanted to know what the tension in the string was, I would have to look at them as two separate objects. And then I could solve either one of our two equations and have the tension, okay? So there are reasons to use both methods, all right? But this system method is often a handy way to look at multiple objects at one time if they're all moving as one thing, or if they're all at rest, say. Right? You can treat them as one bigger object. So enjoy another worksheet, this time on weird combinations of objects and systems and not systems and modified Atwood's machines.